Hey, thanks for coming to the talk. Let's get started. So we are going to talk about two main things like semi-supervised learning and adversarial environment and how each of them coexist. So before the talk, I want to introduce myself and Gaurav. So I'm a data science manager of account security and privacy team at Uber. Previously, I was doing my own startup, and before that, I was working at LinkedIn as a security in the security team. So my interests are mainly applying machine learning security problems and also building scalable infrastructure to support machine learning systems.
Hi everyone, my name is Gaurav. I work as a senior engineer in Uber. Before that, I was at Microsoft for a number of years working on question answering systems and distributed systems generally. My interest obviously lies in distributed systems and intersection with machine learning and NLP.
So let me set the context for the talk. So here we are going to talk about the data science algorithms and process that we did. And for the features, the actual features that we used, I'm not going to cover the details because first it's more like our secret sauce, and the next is it may not be relevant for you because your problem is different. So. We are going to cover the engineering. Gaurav is going to cover the engineering architecture and the challenges. So let's start with what is semi-supervised learning. So it has kind of two angles to it, right? So most of you are familiar with unsupervised learning, where you don't give the labels and try to see the structure of the data. And on the other side, we have the supervised learning, which is a very typical machine learning model where you give, okay, these are positive examples, these are negative examples, and the algorithm will try to find that in the test data set. But what is semi-supervised learning? So with that, there's again two perspectives to that. So one is the coming from classification perspective. So let's say on the top, you see the let's say you have very simplistic example. So you have a positive example and a negative example. And if you ask the classification algorithm, either it be a logistic regression or SVM, doesn't matter. So you draw a decision boundary. It has a lot of options to draw it. Let's say it draws like this, a vertical line. And in most of the areas, getting labels is really hard. And especially that's true in fraud and security domain. First of all, it's a lot of manual process to label the data. So you have a lot of unlabeled data set, right? So if you put unlabeled data set along with the labeled data set, let's say in this example, it looks like this. So a kind of a better decision boundary is more like this, right? Because you can see there's a kind of internal structure to the data, and so you can draw a boundary like this. So this is we call a semi-supervised classification learning. And from the other example that you can give is from going from unsupervised learning to semi-supervised learning, right? So here you're trying to do clustering. You're trying to find internal structures of the data, but you're trying to find clusters that are mostly good or mostly bad or kind of unknown clusters. You don't want a cluster that has both good and bad in it because that's not very useful thing for you. So that's the first part of our title. The second part is the adversarial problem. So what is adversarial problem? Security, fraud, those are pretty adversarial problems. So let's take a very simple classification model. So let's say a traffic sign classifier, right? Let's say someone is working on the traffic sign classification. So the x-axis shows the amount of time you can put in, days or weeks thing, right? Then you kind of keep improving the accuracy of the model. So you go you implement some new technique, then you have a good spike in the accuracy. And kind of after it reaches a stable point, you say, okay, my job is done, and you give the model to the engineer or to implement it in production or use it in a benchmark data set, right? So that your work is done there. But let's say you take a fraud problem, right? So you start with some accuracy, then you put that model into production with some accuracy. Then the attackers find that out. Okay, you have a better model. Then they try to beat your model. Then your kind of accuracy goes down. Then you again go back to work and put a V2 of your model, then again it gets beaten up. So it's kind of a never-ending battle between you and the attackers. So your job as a fraud data scientist, it's not done. Like a model when you build, like it will be there for depending upon which fraud problem you're tackling, it will be only for short-lived model. So you have to keep improving on it. So that's the kind of the adversary component to it. So if you think of in this traffic sign classification, like the traffic signs are not actively trying to hide from your camera. It's like it's already there. Your model doesn't influence the behavior. So I want to give a kind of a real life example. So this is what happened last year. So you can see the time. This was July 4th weekend. So I put up a model in production on Friday before taking my like a 4-day vacation. It had like a better recall like for a while, and by the time I come from the vacation, it's like the recall already like gone down to the nothing kind of a stage. So then we looked into that. We did like a kind of a deep dive and found that the attacker kind of found a loophole where they can make our features, a lot of features null. So the model didn't get enough signal to score the kind of the fraud transactions. So this happens like very often. So the particular problem, the fraud security problem that we are applying this algorithm is account takeover. So account takeover is someone hacks your account either using kind of sophisticated scripting or even like in many cases manually, right? So in the internet, you can easily find a lot of open data, like open password dumps. So hackers can get access to those password dumps and kind of go against Facebook, Uber, Google, those kind of sites and try to validate those credentials. So here kind of shows the, sorry. Yeah. So here you can see the kind of a spectrum of the attack. Anywhere it can go from a single IP, someone is testing like putting just a for loop in the Python and calling your login system, to more sophisticated and targeted attacks on specific accounts. So we typically care about here, like detecting these is pretty simple. Detecting these are very, very hard, especially if you have state-sponsored attacks or criminal underground, like a very sponsored criminal underground. It's very, they are like very reactive, so it's very hard to adapt to their evolution. So next I want to talk about like the clustering algorithms that we used. Since many people may not be familiar with this algorithm, I just want to kind of give an example. So this is a kind of a toy data set, right? So this kind of a k-means just like tries to cluster this and puts a random centroid at each step, and it has an iterative process. So every iteration it tries to find the better center for this each cluster. So k-means is like a very basic clustering algorithm. The main advantage for it runs very fast, but it's kind of a linear clustering algorithm. It doesn't find the nonlinear structure in the data set. And you can see the kind of the sum structure in the data set, but the algorithm just like divides the space into 4 regions. The next algorithm that we kind of played with is DBSCAN. So DBSCAN is based upon the density of the clusters. So here you can see that like it starts from a particular point and finds like all the nearest neighbors to that point. So it has some constraint over like how far it has to look in order to find the nearest neighbors. So the circle kind of shows how far it's looking to find the nearest neighbors. So if it finds enough nearest neighbors, it keeps propagating that cluster. So what it happens is that all these points are connected or like very closely connected. So the clusters like keep on going, and it doesn't like after this there's no more. So it kind of propagated into other clusters. So here you can see that this particular cluster able to find the nonlinear structure in the data set, and all these other points are very noisy. It doesn't have enough points near to them to form a cluster. So for us, like this DBSCAN algorithm worked very good. I think it depends upon the data set that you use. The main problem with the DBSCAN is the scalability. We will talk more about that in the later slides. So what was our semi-supervised clustering approach? So the first, we took the DBSCAN as our main clustering algorithm. And the first method that we use is to do the hyperparameter tuning. So in previous animation, when you looked at, it kind of has this circle where it tries to find the nearest neighbors. That's a one hyperparameter. It's a distance hyperparameter. And the other hyperparameter is like how much minimum points it has to find in order to form a cluster. So there are like two hyperparameters we have to tune. And with respect to clustering, it's really hard to find those hyperparameters because you don't have a very objective function to minimize, like a classification system. But in a semi-supervised case, you have some examples, not every example. So you can use those small set of label data set to find the kind of the best hyperparameter that gives clusters either completely good or completely bad. You don't want, again, clusters that have both good and bad examples. So, and basically it solves the hyperparameter tuning issue, which is like a big issue. The second method that we tried also is a kind of a modifying the DBSCAN algorithm, which was originally an unsupervised method, to kind of, while forming those clusters, try to form clusters that has only good or only bad. So the problem with this approach is that working with weak labels is really hard. Like if you don't know whether it's like a really fraud or really good, the algorithm doesn't work really good. And also scalability is a big pain because the basic algorithm itself is like a O of n squared kind of a complexity, so you are adding more complexity to that. So this is one of the clusters that we had back in 2016. So I wanted to kind of show what we had in 2016 and 2017 and show the difference. So here you are seeing like a lot of clusters. I kind of circle them up. What it shows is kind of a two-dimensional view of the multi-dimensional data set that we had. I think we had like around 10 dimension or something. So here you can see that like these are very different clusters. Some of them are bad. Actually, I didn't label which are bad, which are good. We'll do that for the other 2017 one. So here like you can see that like the clustering, this approach is not only used to label good and bad, but also among the good bad labels, kind of differentiate between different attackers. So if you can differentiate between different attackers, you can like understand what the attack vector is and kind of adapt to that much more better. So this is a similar thing, but it looks like 2017 looks different because first of all, the features that we used in 2016 didn't give any result in 2017. The main reason is the attacks are evolved because we've been building the systems and defending them, and so the attack is kind of evolved. So we have to kind of do a new set of features in order to find these new clusters. So here, like the clusters are, each cluster is given a different color. They are not marked good or bad. We will get to that later in the slide. So some of the main machine learning challenges in doing this work is feature selection. For classification system, you can throw like a kind of a kitchen sink of all the features in, and let the algorithm figure out which are good, right? Like you can use like a L1 regularization to figure out, do the model, like feature selection. But for clustering, that doesn't work. If you put a random feature, even like one feature is random, it completely messes up the clusters. So you have to like manually curate the features that you wanted to work with. And also, it depends upon the type of the feature. Aggregate features works much better than a feature that is like a non-aggregate, right? Like we have some examples here. So for example, features like trip fare or number of trips on an account is a bad feature because it can range a very good rate. Like you can have like users with 1 trip and other users with 1,000 trips. There's not like a good regular, like a small range. But if you have features like percentage of UberX trips a particular user has taken, it neatly aligns it like 0 to 100 range. And if you have all the features in the similar range, it's much better because in clustering, the distance actually is very important. So if you have one feature that is like a very high distance, like a very high range, it screws up the distance measure. Yeah, like you have to find all the features with the same scale. And feature evolution in adversarial environment is important. So even if you, let's say like you get like very good features to find these bad users, if you kind of block those users, the attackers will try to find like what is the signal that these accounts are getting blocked. So they will kind of evolve. So even with the semi-supervised learning, you have to keep evolving the features. And scalability is a big pain because like running a DBSCAN for 10 million data points is really takes a long time. And like k-means, DBSCAN doesn't have any online algorithm. So for example, Spark has a streaming k-means where you can ingest the data in a streaming fashion and it keeps updating the clusters. But for DBSCAN, there's no streaming version of it. It has to kind of go through the entire data every time it has to build a cluster. Then I will give it to Gaurav to talk about the engineering architecture and challenges.
All right, so now we'll be talking about the engineering architecture and how do we accomplish all the good stuff that Karthik has been talking about. Starting with the design goals, obviously before building a good engineering architecture, you want to ask your question, what am I optimizing for? So these are the few of the parameters that we started with. Because as Karthik described, these attack vectors change over time very, very quickly. We wanted minimal human input for unknown attack vectors. So as new attack vectors comes in, the new system should be able to scale accordingly. Automatic actioning support, what I mean by that is once we do detect something bad is happening, can we automatically take an action on top of it? You can think of like a password reset being one of them. Throwing a challenge to the login attempt being another one of them. A second factor auth, showing a CAPTCHA, things like that. Low latency is extremely important because these are synchronous scenarios for a lot of people. So they're actually waiting to log in and take Uber rides. So it has to be a very low latency system. We also wanted to build a system which would scale for other use cases outside of login for which we originally built it. For example, bot signups and so on. And finally, all these algorithms need to be first-class citizens on the architecture and the technology choices that we make. So a good ML library support is really important. This is kind of the high-level architecture that we have, starting from left to the right. So left is where a human would be sitting, basically waiting on an app to log in. Risk gateway is basically our entry point for all kind of interactions that users have with Uber, and we are trying to estimate what to do with that attempt. This is where your credit card charging, all kind of different fraud scenarios plug in. Rule engine is kind of like the heart of this architecture. This rule engine is an extensible UI-driven and an OR statement execution pipeline where data analysts, data scientists, engineers, anyone can go in and put in rules. These could be based on features that we are reading from our stores, or these could be outputs of the models that we have deployed. Speaking of models, that's the ML model service. Uber famously uses the microservice architecture, and this has been blogged extensively, so I would encourage everyone here to go read about fraud architecture generally that we have. Finally, the actions part, that's an asynchronous action that we can take over a user. Maybe it's banning a client, maybe it's actually resetting the password on your account, and so on. Finally, the feature gathering. This is where the low latency system comes in. As you see that during runtime, we are actually just reading features from different kinds of stores that we have pre-computed. So we went with the architecture where we are choosing to pre-compute most of our features, and at runtime, we are just using the keys to read those features back. The challenges that we support in V1 of this project are second factor auth and CAPTCHA. So if you ever got those, we are responsible. This is the feature computation aspect of the problem that we are trying to solve. So for this use case, we are relying heavily on Spark. As you can see, there are two distinct pipelines here. One is a streaming pipeline, and one is a hourly batch pipeline that we run. And I'll go into details on why we had to do that and what choices govern those. Again, from the left, what we have is all these login attempts that I was talking about being ingested from Kafka. This is our in-house Kafka deployment, which we have a schema over. So it's kind of like strongly typed, so we know exactly which data type are we expected. So we ingest those logs from Kafka. Those are the login attempt that we're ingesting. Another interesting thing that we ingest to determine if you're good or bad while computing the clusters is the feedback signals. The signals, the challenges that we were throwing earlier, for example, a 2FA, we're ingesting in real time, are you able to solve those challenges? Are you able to attempt those challenges and so on? So we ingest those feedback signals and the raw login attempts. In this Spark streaming pipeline, we join them over a window of 1 hour. We do feature normalization. We convert some features into the categorical features, and finally run the MLlib-provided streaming k-means. As Karthik described earlier, it's provided out of the box, so it's kind of easy to plug in. Based on this, the output of this algorithm spits out, given the key of each of the login attempts, what cluster do you belong to, and the percentage success of those clusters, and we write all of that to Cassandra. The Hadoop pipeline that we have also computes a lot of batch features, so that goes over the last 7 days worth of data every hour. We read those. We have much more leeway in terms of what we can do there. So we run our heavy lifting algorithms there. One thing to note is because of the limitations of DBSCAN on Spark, we are actually using just sklearn version of it, so it's all on one machine. There's nothing fancy there. Because of which we have to kind of limit our search space, what we can run on. So we prune a lot of data that we ingest, primarily based on heuristics. So in our case, we said we were able to prune 90% of the data that we were looking at. Finally, parameter tuning is obviously a big area that we have explored in. And this is mostly around parameter tuning of DBSCAN algorithm itself, so epsilon and min points that Karthik was talking about. Output of this also gets written to Cassandra. Cassandra brings us a nice benefit. It's a good key value store that we have at Uber. Scales pretty well, hundreds and thousands of QPS. And at runtime, we're just doing a simple readout of that. The nice thing about Spark Stack that I personally found was the reuse of the code that you can do from streaming and in batch. So most of the code is similar between streaming and the batch. So that kind of works well here. Now I want to talk about some of the engineering challenges that we faced here. So when I started knowing Python more than I know Scala, I started with PySpark for the streaming use case, and quickly realized it was quite inefficient. So once we launched that in production, we saw it lagging beyond the window size that we had. So at that point, I decided to switch to Scala version, and that seems to be doing fairly well. So in streaming use case, as far as my benchmark goes, Scala outperforms the PySpark. The DBSCAN limitations we have talked about. For this, we will talk in a second what we are doing about it. Window aggregations was limited to 30 minutes. Actually, that should be 60 minutes. So our production deployment today does window aggregations on our data set for 60 minutes. Of course, it depends on the amount of data that you have and so on. But we could only do 60 minutes worth of streaming aggregations. Finally, the joins for the feedback signals are only allowed within this window, obviously, in Spark. So the feedback signals, like 2FA, if someone is taking more time to solve those challenges, we are going to miss that data. So joins are slightly challenging in the streaming use case, but still doable. I hear with the new version of the Spark structured streaming coming out, this may be better for use. So we'll check that out once it GAs soon. So production setup, just the numbers that I've said earlier. 7 days worth of data, runs DBSCAN hourly. Streaming data set, 60 minutes, moving window. We do streaming k-means. We use the feedback signal success ratios and mark the clusters as good or bad. What that means is if the majority of the points in a cluster are considered to be good, beyond a certain threshold, we mark the entire cluster as good. And same for bad or unknown. So what we do is for bad clusters, from the rule engine that we have, we can choose to throw always a challenge to the users. For example, if we know that this is a bad cluster, we can throw a 2FA challenge, or we can deny the login outright. For good clusters, we still want to collect the data, so we throw a very small percentage of people a challenge that we know they can solve. And finally, unknown clusters. This is something that is the most useful here. For new attack vectors, for people that we do not know what's going on, we choose a small percentage of that population to throw a challenge and collect feedback signals. So basically, it kind of completes the whole loop. We can throw a challenge, collect data, mark them, and throw again, and so on. So this is the results out of this. So red ones are bad clusters that we found. based on the heuristic that I just described. Good clusters are green, and blue ones are unknown. So in this case, you can imagine anyone who belongs to the red cluster to get a second factor auth challenge. A good one, no impact, they just go straight away for most of the time. And for blue ones, this is where it's most interesting. We will choose, let's say, 5% of the population to get a challenge. And out of those, we'll see how many of them are solving correctly, which is where in the next job run, they may be moving to a different cluster. Basically, they start belonging to a good cluster or a bad cluster, and so on. Kind of completes the whole picture. So this is the most interesting part, which we are working on recently. Due to all these scale challenges in DBSCAN running on single machine and having lots of problems with huge data sets, so we are experimenting with Faiss library from Facebook. This has been open sourced very recently. So we are experimenting on a GPU-based DBSCAN, and early results look very promising. So how to read this chart is going by the number of dimensions. This is the number of features that we have for each point. And then another axis is the number of points in that run. And on the y-axis, you can see the factor of improvement that GPUs are bringing compared to the CPU version of it. So as you can see, for starting with 100,000 points, we are 1.5x or somewhere in there, and goes all the way up as the dimensionality goes up. So from our findings, if the dimensionality of your input features goes up, GPU impact increases much more. As the number of points go up, the GPU still outperforms CPUs beyond a certain number of points, but not by as much factor. This is looking extremely promising, and it unlocks a whole bunch of scenarios for us, so we will not have to do the early pruning that we had to do before, and so on. Do you want to add something?
Thank you.
Thank you. Any questions?
A couple of questions. With all this, what do you think your success rate is so far? There is a whole bunch of users that they have bad passwords because they were subjected, but you send them the authentication or the two-factor authentication, but they don't reply to you. So you know that it's not them, right? Are you able to quantify your success with this one?
Yeah. So in order to measure the account takeover, it's difficult because a lot of times there's no changes to the account is made, so the user doesn't know the login actually happened. So we are working on how to get the feedback from the actual users to measure that. And this is just one of the models that we have in production for stopping a account takeover. And we kind of have a combination of all these models to act on them. And we have like a lot of other ways, right? For example, if we totally miss the account takeover and actually happen, so probably if the bad fraudsters actually take a trip on your account, and you will see that in your bank statement, and you will complain to the Uber, right? At that time, we will know, okay, we missed that. So we have kind of a feedback loop, but those are takes long time, up to 60 days to come back. We wanted to kind of have much more tighter feedback loop.
To be more specific, so we ran this algorithm, how much lift it's bringing compared to all of our other models. So on top of everything that we had based on our analysis last year, it was around 10% or so.
That's great.
Which we were previously missing.
Yeah. And the second question is, have you considered device fingerprinting for account takeovers?
Yeah, there's like a lot of other things that we have, device fingerprinting.
Does it work?
Yeah,
I wanted to ask about device fingerprinting.
It works to some extent.
So the device fingerprinting obviously is used a lot for this use case. However, in experience, there is no standardized way of doing device fingerprinting. So we always struggle with a whole bunch of fingerprints, different versions, different OSs have different identifiers. So we struggle more with the reliability of device fingerprinting than the use of fingerprinting. Cool. All right, thank you.
Thank you.
Thanks for your time.